Okay? So again, hopefully you guys are writing down this goal, but again, you guys will be able to describe subsets of real numbers and identify and evaluate functions and state domains. Now some of this stuff will be a review from Algebra 2, okay? If you don't remember anything from the summer taking place, hopefully, some of this stuff will start coming back to you as we go through it, okay? So here we go. So let's start off with functions. Real numbers are used to describe quantities such as money and distance, okay? The set of real numbers, which is represented by this like shadowy R, this, I don't know what type of like double bar R, includes the following subset of numbers. And what you guys have there is a diagram that represents all the different classifications for the types of numbers that are out there, okay? You have your natural numbers, all right? Your natural numbers, which is represented by that N, as you guys see over there in that table, don't you? Okay? That N represents your natural numbers. Those are your numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Basically, all of your positive whole numbers, okay? Now, your whole numbers are all of those positive numbers and also 0, okay? Those are your whole numbers. And if you notice, the natural numbers is within the whole number circle. Because if you think about it, all the natural numbers, all the positive numbers, are basically what whole numbers are as well, except the only whole number that's not natural is, what again? 0. Then you have your integers. Your integers are not only your natural numbers, all your positive numbers, it's not only 0, but it's also what? Your negative numbers as well. So it's negative numbers, negative whole numbers, positive whole numbers, and 0. Those are your integers. Okay? And that right there is represented by not an I, but what letter? C. Okay? And whole numbers is represented by what letter? W. Okay? Now your rational numbers. Your rational numbers include all of your integers, all of your whole numbers, all of your natural numbers, but also what type of numbers? Does anybody know? Rational? Unimaginary?
Fractions.
It would be your fractions or your decimals that can be converted into fractions, okay? So that's where your 1/2 falls, 3/4, 7/5, okay? But that's also where those decimals like 0.33 repeating also fall into. Because what's 0.33 repeating as a fraction? 1/3. And does anybody know what 0.125 is? 1/5. What's 0.125? What's that? 1/8. It is 1/8. Okay, so also being able to recognize those decimals that can be converted into fractions is also a good thing. But they fall under the rational numbers group, of course, along with all your whole negative numbers, all your whole positive numbers, and 0. And that's represented by the letter what? Q. Then you have your imaginary numbers that do not have any of these properties right here in this circle, in all these circles. Okay? Somebody give me an example of an irrational number.
Infinity.
Dang it. What? Say again?
I.
No, that's imaginary. That's outside the circle. It's not it. Irrational number. What is an irrational number? Example of irrational number, anybody? Think of all the numbers that you know that don't fit in any of those categories that I just said.
Negative fractions.
No, that would be a rational number. That would be rational number.
Improper fractions.
That would be rational number.
When?
Okay, come on now. Think of what other number do you know?
All the numbers.
That falls in the whole category. Come on now, I know somebody here knows the irrational number. I know somebody here
Give us a hint.
knows an irrational number. You use it often. Right? Pi. I'm about to pause it. Alright, yes, it is pi. Okay, pi is an example of an irrational number because it is a non-terminating decimal that just keeps on going. Okay? Also, the square root of 3 or the square root of 5, those are also irrational numbers because they aren't perfect squares and they're basically continuing decimals that don't end. Okay? That's where your irrational numbers fall. And all of these are basically all defined real numbers. I are your imaginary numbers that exist outside of this circle. Okay? So there's your classification of all the different types of numbers and where they fall. Okay? Now, so when you guys see those symbols on your SAT and the ACT, when you take them, you'll know what they are referring to, okay? They use Z a lot. And Z stands for what? So, these and other sets of real numbers can be described using set builder notation. If you have me, Ms. Childress, or Ms. Carranza, we did go over set builder notation just a little bit, okay? We concentrate more on interval notation. You're gonna get real comfortable with both now in pre-calculus. Other teachers, I don't know what you guys cover. Alright? But here's an example of set notation. And this is generally how it translates to. Okay? It translates to the set of numbers x. Okay? So, this first part with the curly bracket and the x relates to the set of numbers x such that represents the bar that separates the x from the given properties. X has the given properties right here. Those are the given properties. So basically, x is greater than -3, but less than 16. That's the given property of x. And x is an element of the given set of numbers. That is the last part. All of those pieces make up set builder notation. Okay? You have your variable, you have your property, and then of course, the elements which the set of numbers fall in. And again, this is just one way to represent a set of numbers. So, let's look at a few. We're going to look at a few together. You're going to try some on your own. The first one, we have 8, 9, 10, 11, ... One person raise their hand and tell me, what does the ... mean? Raised. Okay, that was like collectively. Yes, it means it continues. Keeps going. Does it ever end? No, so basically it can go all the way up to what number? Infinity. Okay? So, but I'm starting where? At 8. So if I'm going to write this in set builder notation, I know I need to have first a curly bracket, I need to have an x, and I need to have a bar. So this right now reads the set of numbers x such that. Now I need my given properties. My given properties is what represents my problem here. And most of the time it is written as an inequality. How can I represent 8, 9, 10, 11, 12, 13, 14, 15, all the way up to 7? But is the 7.5 included?
Yeah, so everything
Very good. Everything greater than or equal to 8. So we would write that as x greater than or equal to 8. There's the given property. All the values that are greater than or equal to 8. That's 8, 9, 10, 11, 12, so on and so forth. Now we need to have our given set of numbers. And this kind of tells you something. You can kind of figure out what numbers come after this, right? 12, 13, 14, 15, 16, right? All of those are examples of what types of numbers?
Ooh, I got this one. Natural.
Natural numbers. Not rational. And you know it's not rational because it's not like you have 17 halves or 21 halves or anything like that to show that there are fractions in between. It just wants those whole positive numbers. So that last little bit would be x. This E here, which represents elements, and then the double bar in a closed curly bracket. Does everybody see how that works?
Wait, what double bar?
Like, it's the end that's on your paper. So it's it's like that first part is like
So it's
A
up
block.
and then a double bar across.
it's like a block here, and then the end is normal there, but then it's like a block there. So it should look like that.
It's the opposite. It's a block in the middle.
Oh, it's a block in the
and two
middle.
lines
Nonsense. But it's not a normal end, okay? Please do some way to distinguish that we're talking about natural numbers here and not the letter N. Everybody understand that? Okay. Mimi, you had a question?
I was gonna say, do we have to write down my side?
Yes, please distinguish between your regular N and this natural number. Okay? So all of them are set up the same way. You have your curly bracket, you have your variable, you have your such that bar. Now, B is pretty simple, okay? It already tells you your properties. It's all your x's less than 7. So that part comes after the such that bar. So we have the set of numbers x such that x is less than 7. And now x is the element of what set of numbers?
It's
All right, someone say
integers.
it is not integers. It's not rational.
It's everything less than
It's
7.
everything less than 7. So those are your whole numbers. Those are all your integers, positive and negative. Those are all of your rational numbers, fractions, negative
Real
fractions.
numbers.
It's all your real numbers. So that includes the square root of 3. The square root of 3 falls is less than 7. So it's all of your real numbers that are less than 7. So we need here R. And the reason why A and B are different is because first off, they already alluded to the fact that they only want your whole numbers here. Had they wanted your rational ones, they would have put in that decimal in between if they wanted you to indicate your rational numbers, not just your natural numbers. Here is anything possible that's less than 7. Negative, 0, positive, all that. Some of y'all, check your slang. Okay? Fix it. Last one, C. All multiples of 3. First off, you guys know your multiples of 3?
3, 6, 9, 12, 15,
3, 6, 9, 12, 15.
21.
Good stuff. But I got a question. Is negative 15 a multiple of 3?
Yeah.
So we know that it's our positive multiples as well as our negative multiples. So we know already that we are going to be dealing with our integers here, okay? But how do I represent this property here, all multiples of 3? How would I represent that, okay? So I know I got my curly bracket, x, bar, comma, curly bracket.
Yeah.
How would I represent all of your multiples of 3? Does anybody want to take a stab at it? How would I represent that?
3 to infinity.
What do you mean? Like, so did you say 3 to infinity, so you mean like kind of written like this, so if you have 3 and then infinity there?
Yeah.
Okay, gotta be careful, because we don't want only our multiples of 3. So we wouldn't want 4, but just 3, 6, 9, 12. Very, very close. You are right. Just a little bit. You got x equals 3, but you don't want to put x.
Why?
Wait, are you
Yeah,
asking
yeah,
why?
Yeah, you want to put why. You?
Wait, are you asking
No,
why?
no.
Are you saying the variable
Yeah.
y?
Yeah.
Okay. Yes, a different variable than x.
Something other than x.
Something other than x. Okay, so it could be y, it could be n, it could be W, okay? But it would need to be a different variable than what your set of numbers represents, okay? Now this last part, an element of your given set of numbers. This is different, and the reason why is because you're looking for all your multiples. X is equal to a particular number. It's gonna be 3, it's gonna be 6, it's gonna be 9, okay? We're skipping all of your, rational numbers, like all your fractions. We're skipping all of your real numbers that aren't whole numbers. So in this case, whatever other variable you use, in this case it's y, is going to be the element of all your integers. Because that is the thing that we're plugging in to determine what exactly our set of numbers is. Questions?
How long are we going to do this? Similar to that,
We're going to do 3 more examples and then we're going to Questions? Let's try those on your own. I want you guys to try those on your own. After each one, I would like you to compare with your mates, person you're sitting beside, see if you guys got the same thing. If you're sitting alone, maybe the person behind you or in front of you. All right, some good conversations, okay? You guys compare answers. I'll be doing that a lot, okay? If I'm not whiteboard checking where I want you to show me, then I'll, after a little bit while working, work with the person that you're sitting beside or the person who's behind you, whatever, okay? That way, maybe we can kind of, save a little time on this end going over a problem. So, D. I'll take a volunteer. Who wants to give me what they put for D? Lacey.
X such that X has given properties, or X is greater than 1, or greater than or equal to 1, sorry.
Very good.
I don't know what was happening. And then X is the element of natural numbers.
And I need my preference. Yes. Very good. Okay. That's proper. And the way she said it was good as well. She said X such that X is less than or greater than or equal to 1, and X is an element of a natural number. Okay? That's exactly how you would say it. Very good. Who wants to do E? I'll take a volunteer this time. Ian.
X such that X is less than or equal to 3, comma, X element real number.
Very good.
No, it's
Yes. Look, this is my handwriting. I apologize to those who've not seen it before. No, it does not get any better. Okay? So, watch it. Okay? Okay.
Okay, you got it clearly back. Alright, X such that X is equal to pi Y. Y is the element of irrational.
So Q, I, which one?
I.
I. Alright. Gotta be careful. What are my multiples of pi? Run them out. What are my multiples of pi?
Like this.
Well,
Q.
But okay, first off, multiples of pi, that's pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. Also, negative pi, negative 2 pi, negative 3 pi, so on, so on, and so forth. So y has to be an element of not q, not rational numbers, but
Real number.
integers. Yeah, because look at what we have here. It's y. What number can I plug in for y to get a multiple of pi? So that means I'm plugging in 1 for y, I'm plugging in 2 for y, I'm plugging in 3 for y. All of those are examples of integers, because I can also plug in negative 1, and negative 2, and negative 3, and that will give me a multiple of pi. Yes, ma'am?
Why does it say Y when you the E for that one, but for C it says
Did I miss something? It was y. It was, yeah, that's y.
E?
It said my handwriting. No, it was my handwriting. Hush. Okay, questions before we move forward. So when you guys see these on the SAT and the ACT, you'll know exactly what they mean because they do use these. Okay? Now, set-builder notation and inbuilt notation, they're like brother and sister, okay? Because they both come from the same family, they both represent the same thing. Okay? It's a way to represent a set of numbers. But with interval notation, which you're probably more comfortable with, you have a brackets, meaning that the endpoints are included, and then you have parentheses, which means they're not included, okay? And so when you write a set of numbers in interval notation, you gotta look at the symbols, okay? If you have a less than or greater than, am I gonna use the brackets or am I gonna use the parentheses?
Let's say you use.
I'm gonna use parentheses, because think about it,
Oh, that's true.
is negative 8 included?
No.
No, it's not. Think of it also as a number line. If I asked you to graph this, like old school graphing, like Algebra 1, would this be an open circle or a closed circle?
Open.
And at the 16, would it be open or closed? It'll be closed. So if you can't remember, go back to what you know. Draw a number line. And if X is in between, that means I'm shading where? In between. So to represent this as interval notation, an open circle means parenthesis, a closed circle would mean what?
Bracket.
Because it's included. And then all you do is fill in the numbers. Okay? And it works for all of them. You can do it that way. Here, B, X is less than 11. You have 11. Is it an open circle or a closed circle?
Open.
Open. And I'm shading left or right.
Left.
So in interval notation, what number is all the way to the left?
Negative infinity. So it's parenthesis, negative infinity, parenthesis 11.
Is an 11 around the parenthesis?
Yeah.
A parenthesis around the 11 because it's an open circle, and negative infinity, just like positive, is not a defined number. So we gotta put parentheses. You always put parentheses around our infinities, either positive or negative. Okay? Now, this number line that I'm drawing, you don't have to draw it. If you're good with recognizing, okay, no equal then symbol is a parenthesis. An equal than, an equal to symbol is a bracket. You can do it. You don't have to draw the number line, but I'm mostly doing this for those who might have a hard time trying to see it. C, little tricky. Here's my number line. I have 5, and then I have 16. Now we're on a number line. Remember, smaller numbers are to the left, larger numbers are to the right. And this is how they can really trick you. Okay? Because I really was about to put 16 here and then 5 here, and that was going to be all types of wrong. Okay? Is it an open circle or a closed circle at 5?
Open.
An open circle. Is it an open circle or closed circle at 16? Close. Now, I'm less than 16 or I am greater than 5. So, less than 16 would be going this way,
So you would do
and then greater than 5,
So it's trying to trick you because
It's going
an or,
this
but
way.
It's an and actually.
no, it's an or. How would I represent this in interval notation?
This is different.
And would you, like two different answers?
Like two different things with the U in between?
Oh, I hate the U.
No, it wouldn't be that.
You would put an or.
Or U, that's the
You would put, oh, you could put an in between.
Think about it. Is all the numbers less than 16 or all the numbers greater than 5? Say again, Cheyenne.
Oh man, smarty pants.
It's negative 250. It's all those numbers. Because if it was an and, then it would be where they overlap.
Oh, that makes sense. Okay.
If this was an and, it would be just this part in between. Okay?
Yeah, but
But
it
since
keeps
it's an
going, it's
or,
not
it's
just that.
all those possible numbers. You guys see that?
Yeah.
Huh? If this was x was greater than or equal to 16, or x is less than 5, this would have been with the union. And then you do it opposite ways. Let's do this one, okay? I don't know, do you have space? Maybe you can add it in somewhere? Okay, add this in, write this one in. Let's make this C and a half. Okay? Because I got D on the next page, so I can't use D. I want to put this in interval notation. Okay, so on my number line, here's 5, here's 16. I still have an open circle at 5, but this time I'm going to the left. And I have a closed circle at 16, but this time I'm going to the right because it's greater.
That's when you use the U.
This is when you
There's
would
a
use
fancy
the
word for that. I can't
Union.
remember. Union. Yeah.
Okay.
That's a pretty fancy word.
How do I represent just this part?
You put
Negative infinity,
negative infinity, comma 5.
parentheses.
Both
Yeah.
sides.
How do I represent this?
Union.
16.
Bracket.
16 with a bracket,
Comma infinity, parentheses, union.
and then a union in between, and then that would be how you would represent that set of numbers. So, okay, so you gotta be very careful. That was a tricky one. So you drop it. Connor, what'd you get? Yes, you did.
I got both of them going left on the little line thing.
combine one. Kind of tricky. Okay, did you have -4 first, and then -1, yeah?
Yes.
Okay, cool. So, what you have at -1? Connor?
At -1.
Yeah, like, circle-wise.
Open.
And then at -4?
Close.
Okay. So, think of it like this. I'm looking for all the y's. Since y is in between these numbers, my shading needs to be in between those two numbers. Okay? So now that I got my shading, can you do it now? Okay.
We don't have to do it.
What you got?
I got the bracket,
Yeah?
-4,
Uh-huh.
1,
Yeah?
or -1,
Oh, yeah.
and then
Is he right?
Yeah.
Yes, that he is. Good job. All right, here we go. Here's the next one. All right, let's come back together. Sean, what you get?
I got, bracket, 3, infinity, parentheses.
You right?
Yes.
Yes, he is. Good stuff. One more. Here we go. All right, let's bring it back. Tina, what we got here?
Parentheses, negative.
Back in here.
Parentheses, negative infinity, -2.
I jumped. You got a question, right? Okay.
A parentheses, 9, infinity,
Very good. And I like that you put it in order too, okay? If you did not put it in order, you're not technically wrong, but you're not all the way right, okay? Remember, your negative numbers come first before your positive numbers, okay? So just be careful on that. It looks like a test. I wouldn't count you wrong as long as you have the U, you have the parentheses and everything like that, but let's practice good habits, yes? Good job. All right. Questions on interval notation? Moving forward. A relation is a rule that relates to quantities, okay? It is a rule that relates to quantities, okay? Such as like a bank account number and the money in that account, okay? Two quantities. Now, a function is a little bit different from a relation. It is a set of ordered pairs in which no two different pairs have the same x value. So a function is a set of ordered pairs in which no two pairs have the same exact value. So the example I just gave about a bank account number and the money in that account, that is not a function. Just think about it. Today, my bank account number has, I don't know, $100 in it. Tomorrow, after I get gas and grocery shopping today, that same bank account number is going to have like $200, like $2 in it. Okay, so that right there, that's an example of relation and not function. You have different y's but for the same x. Okay. Graphically, this means that no 2 points of a graph can lie in the same vertical line. So if I gave you a set of ordered pairs, right, a set of points, and you graph them, if 2 points have the same x value, and there's a vertical line that can be drawn and touches both of those lines, it's not a function.
That's how you know by the vertical line test.
That is.
Everybody should still be thanking me last year because you would have never done it.
That is the vertical line test. Yes. Okay? The vertical line test can basically tell you by looking at a graph if a relation is a function or not. Okay? The next two examples are back to back and it deals with both of these concepts. So whether you have a function or not, and then of course function notation. This should look familiar. The f of x should look familiar. That means function. Shaking the things. It can also be written as y equals f of x. Okay, so this is what f of x is. It's y. Okay, x is your independent variable, y is your dependent. X could be anything else, but y is dependent on it. Okay. So we're going to look at a few examples. We're going to figure out some relations are functions, and then we're gonna actually look at function notation, things like that. This stuff should be familiar. Yes? You've seen this before? My kids were shaking their head looking at all the books I didn't have. Yes? Okay, cool. So, we got 3 examples, A, B, and C. We're trying to determine if each relation is a function. The first one is a set of points, okay? I'll take a volunteer on this one with a raised hand. Gabby, is this a function?
Is it not a function because of the vertical line test?
Okay, the vertical line says which set of points? Is it not passing? Wait, okay, that made no sense. So, you say it doesn't pass the vertical line test. So that must mean that 2 points like are crossing a vertical line at the same spot.
Yeah.
Which points are those?
All of them, except for the
Oh, I'm looking at this one.
Oh,
Were you looking at this one?
yeah.
Okay, well let's jump. She did B, okay, but she's right. This one is not a function. It does not pass the vertical line test right here and right here. That's one example. So yes, this is not a function. Okay? What about A? Faith?
No. Because there's 1 and 2 and 1.
This one is no because of this right here. You have the same x with 2 different y's. That cannot be a function. You have to have you have one x for one unique y. One input for one output.
So the y can be
The y could be the same, but the x's would have to be different. Because think of it like this. If I had -5, 2, and -4, 2, and -3, 2, these still are passing that vertical line test, aren't they? But if I had,
Teachers, please pardon the interruption.
but if you had -2, 3, and -2, 2, and -2, 1, that would not pass that vertical line test.
So,
Okay.
if you have the same x for 2 different y, you can
Ms. Anderson.
Correct. Yeah. Volunteer on the last one. Who has the last one? Tina. Sure.
It's a function.
It is a function. Yes. Because if you look, every x has 1 y. Simple enough, right? Okay. This stuff should be even simpler. Alyssa, what does this mean? When you see something like this, what's it mean?
Can I do that?
Oh, hold on.
You plug in.
So hush! I'm asking, listen, she's telling. What do I need to do? Exactly. I need to replace every x with the 6, okay? So that's what I'm going to do. So I have 6 squared plus 8 times 6 minus 24. Now, yes, I include the parentheses because I would hate for that to have been a -6, and then you try to square it and say it's -36. No, you are squaring a -6, okay? But it's positive, so we ain't got to worry about that. But it's good practice. 6 squared, anybody?
36.
8 times 6.
48.
When we add those together and then subtract, we get 60. Because we don't need no calculator. Okay? Quick thing to help you out. 48 minus 24 is 24. 36 plus 24
6.
is 60. Okay? Good.
One time, sorry, ready.
It has. Back together. We're back together here. When you plug in, be very, very careful, you guys. Now, I put the parentheses in the first one for a reason. Ones like this, you gotta remember that you're squaring not only the x, but also that -4, okay? So this right here becomes a 16x squared, then a -32x, then a -24. You don't have to keep going after that. It just asks you to evaluate. So once you've plugged in and you simplify by combining like terms, you're done, okay? Down here, be very careful. You have to remember that when you plug in a binomial means what? Anyone?
2
what?
terms.
2 terms. When you are squaring a binomial, you have to remember that you need to FOIL.
Isn't it so sweet?
I think I got it.
Okay, too much.
So you have to FOIL that out. Do not forget that. So this becomes a 25x squared plus 20x plus 20x, which is a 40x. plus 16. So remember, first, the outer is 20x and the inner is 20x, let's say get 40x. Go ahead, write that out. Over here, distribute. 8 times 5x is 40x, and 8 times 4 is 32. Minus 24. Last thing I need to do is combine like terms. So 25x squared
Plus 80x.
plus 80x plus 24.
And you're all back.
If we did not get this, did we see when we made our error? Was it the forgetting to write it twice and foiling?
Nope.
I gotta be careful. Okay? Gotta be careful of that. So on the next one, f of 12, when you plug 12 in and simplify, do anyone get this one?
So far, I did.
Yeah.
I got it.
Yay!
Did you guys get this?
Woo!
Good stuff. Please tell me at the bottom you got 36x squared.
Yep.
Good. You gotta remember, so this is a 12x plus 3 over 36x squared minus 12x plus 1. I can't go any further than that. Yes? I was going to say that. 12 can't cancel out because the top is having a 3 added to it, and then the bottom is having a 1 added, and then it's being subtracted from that. Now, if everything was being multiplied, then we would be able to cancel out. But anytime anything's being added, you wouldn't be able to cancel out.
Alright.
Yep.
You ready to go home?
And then the last one. I hope I was able to give you guys enough space to do this one because you would have had to foil here again.
Can I just say it?
Did you get it?
Yeah.
Okay. If you got this one, you guys listen up. Let's see how Kay is.
Possibly.
Possibly. Okay, what you got?
Negative 6a plus 19.
Yeah.
Over 9a squared minus 54a plus 8. Is that right?
You guys get this?
Oh.
Uh,
Is that right?
the numerator is right. Let's double check the denominator. You guys, let's work this one out. I want everyone to work it out. We're checking that denominator. Okay, so this should have been a 42a, a negative 42a, and this one should have been a 49. Be careful on that.
How did you get 42?
Because negative 24 and negative 24a made negative 48, and then you're adding.
I said 40.
Don't forget about that negative. When you distribute two negatives, they make a what? A positive. Okay? Now I know we're not all looking at the notes, but we're gonna stop there, okay?
So we can like just